what we will go ahead and do is kind of scale up the difficulty. First a little bit, and then very arguably a whole hell of a lot. So what we can quickly do with these is we'll take the models with our ethanes, and what we're going to turn them into would be butanes. Can you accept models being thrown at you? You said yes, so there you go. Should have warned you.
I wasn't ready right then.
My fault. Okay, because you two are kind of close. I'm going to throw it in the middle and then let you guys fight for it. You two are kind of, oh, you're not even going to let me throw it in the middle.
Catch it? Ooh, that was nice.
And the three of you are all nice in the back. And since Lynette's sitting in the middle, should I not throw it at you? Okay. So this should allow you, well, I'm throwing it in the middle for the two of you so that you could theoretically come together to coalesce around it and look at it and use it and think about it. If you don't want to, that's fine too, but that's the intent. Yes. So if we're going to look at a butane, we could draw our straight chain formula. We've got an abbreviated formula with the CH2 in parentheses. All of that you're responsible for. Thinking back to the exam, you're responsible for that. I don't like that format. You are responsible for it. That's how you would see things. So you will see probably one or two questions saying, here's a formula. What structure does this look like? And now I'm expecting you to be able to do that interpretation. Right? The vast majority of the time, I won't give you those formulas because those formulas aren't easy to interpret, and I would rather you be interpreting drawings and structures than formulas. Okay, so remove one of those steps in that interpretation. Okay. So if we built out our butane, okay, which you theoretically now have, where we're saying the blue atoms are now the CH3s, okay, what I want you to do is to rotate the sigma bond between carbon 2 and carbon 3. Right? And the blue atoms will help because then you can start to see their relative orientation will change kind of around that molecule. So I want you to kind of rotate through those and get a feel for what it can potentially look like. Okay? We can get the system where it can sit down nicely on the table, all nice and symmetrically, or it's a little bit off kilter. Okay? And then also, we want to consider what it looks like as a Newman projection. So remember, in the Newman projection, what we were talking about doing is grabbing our molecule. So if these were our black atoms, and there's our blue bonds. Okay, I'm going to put in a red here as saying this is my front, that if I grabbed that carbon and I brought it kind of forward, okay, out of the plane at us, I believe, Sophia, you were the one that complained about this, like, where's my eyeball? There's my sketchy looking eyeball. Okay, looking at it from that side. What would we see? Okay, well, what we would see is our front atom as a dot. We'd see our blue bond straight up from it. The black atom is in back, and remember we're showing the black atom, or the back atom is a larger atom, reverse perspective, and then we have that blue bond straight down from it. Kind of, sort of. That doesn't have a lot of information in it because what has it hidden? I would argue the main black line is actually in there. Okay, there's that first line, call that 1. This one I would call 3. This black line 2 is kind of there, it's just behind the red atom, so I can't draw it, but it's going straight back out of view. Okay, so to me, I would argue all of those lines are there. You do have an argument saying bond 2 isn't visible. Okay? But there's a larger issue here. There's a lot more information that's hidden within this structure that should be shown, as we'll see in a second. So what is that stuff that's hidden? Why are you blinking crazy at it?
I'm just confused on this.
Okay, so, and this is where it can be helpful with the model.
Like the formula.
So if we look, you got the blue atom up and to your right, right?
No, like why are there only two if there's 4 carbons?
4 carbons, blue atom, black atom, which I've called red, up there, the red dot, black atom, black
these
dot.
are all carbons?
We're calling those all carbons.
Oh, I thought they'd be the same color.
So yeah, we would do it as the same color, but I couldn't find the same color balls,
Okay.
actually. So I just turned them into blue and said that's what we're gonna work with.
Okay.
Does that make sense?
Yeah.
Right? So there's more information that's missing from this. From both drawings I have up here, your models have vastly more information than what's up here. What's that missing information?
It's 3D.
Yeah, make the argument that it's 3D. I would accept that. What else?
Electron orientation to each other?
But I would say this is showing electron orientation. Each of those lines represents electrons, and I'm showing where those blue atoms are relative to each other, connected through those lines. What else? Devin's not the only one in the class.
Doing my best here, guys.
What else is missing? What was that? Yeah, none of the hydrogens are shown in this drawing. Okay, they're implied in your model kit. That's what those gray bonds are going out to hydrogens. So if we were to better draw our side view, okay, we could go through and say we had a wedged hydrogen coming at us, a dashed hydrogen going away, okay, and that 2 is now in my way. The wedged hydrogen coming at us and the dashed hydrogen going away. Great, that's on the line angle. What does that look like in the Newman projection?
Stuff going out to the side.
Yeah, so draw it. Stuff going out to the side, but make sure that you've got the appropriate connectivity for that stuff going out to the side.
Shouldn't these ones have that?
What?
Shouldn't these have hydrogens?
They should technically also have hydrogens. So for the sake of people recording at home, the question is asking about should the blue atoms, or what we've labeled as B on our screen, should those also have hydrogens? Yes. Those are tedious to go ahead and put in, and they're outside the Newman projection. So we actually don't care to put in those hydrogens because it's not necessary for the sake of this.
Okay.
If, however, you want those hydrogens, I can give you all the sticks to put in there.
Yeah, I do.
You do? Yep. You want purple or gray? Does anybody else want the sticks to represent our hydrogens on the blue atoms? And it's fine to have them on there, it's fine to not have them on there. I would actually argue it's going to be cleaner if you don't have them on there. So I think it's a good thing that you're putting them on there, because then we can talk about why we would choose to put them on or not. Wow. Draw your hydrogens. Where are they? On the Newman projection. So we've got 2 drawings up. We've got a line angle and we've got a Newman. You should be able to draw the hydrogens on the Newman projection. Sorry. Yep. Oh, you had it. Oh, yeah. Yeah. No, not that one. Yeah, not those ones. So the 2 that you've got angled up here, you actually don't want to connect to the front atom. By drawing that line all the way through, you're connecting it to the front atom. Is this hydrogen connected to the front atom? And that's where the model kit would come in handy, but she's looking at it, it's connected to the back atom. So yeah, we'd want to show it like that. Yeah, now you got it. You got to finish out the other half of your molecule, but yes. Yes. Okay, so this drawing isn't necessarily bad, but you'll note it's not the exact same that's shown up there. When you draw the B connecting through and the B connecting through, this drawing makes it look like they're both connected to the exact same spot. They are not. If we look at the line angle, they're connected, one's to the red carbon, one's to the black carbon. Your drawing needs to better reflect that so that you can actually do proper interpretations of the three-dimensional drawing. Does that make sense?
Yeah.
So this is where we call that back atom a circle. So cool. The point on this is the model kit is supposed to really kind of help us drive through this. And since I don't have a model kit in my hands, I'm just going to steal it from you guys. Okay. And if we go through in a line, we've got our blue atom, which we've now said connected to what we're calling on our screen is the red atom, black atom, blue atom. So the blue is up and to the left, your left, is that right? Okay. The other blue is down and to the right. Okay, it's inverted. Okay, so that's what we're looking at. When we change our viewpoint on the molecule, what we're now doing is saying, I want to look down the carbon 2-3 bond. So that's what C2C3 means. It's referencing carbon 2 to carbon 3. So now what I want to do is cite like that. Okay, and particularly for your drawing, that's exactly what you drew, but it now removes that connectivity information that we want to see within it. Okay? So a common interpretation, and I'll try and move it around so that everybody can actually see this viewpoint, and if you've got the model, theoretically you can align it. Okay? None of you are making eye contact with me, so I can't aim it at you. Okay? So an initial view or an initial interpretation might be something kind of along these lines where we say blue is connected, blue, and then we've got kind of this star pattern coming out of it. Okay, the problem with that is now all of those atoms look like they're connected to the exact same center atom. That's not the point, okay? Because they aren't all connected to that exact same center atom. So what we do is kind of backtrack out of that, and we decide that our front atom we'll call a dot in the middle of our structure, and then that back carbon we'll call a big circle behind it so that it stands out. Okay, so then we would go through and look at kind of the black atoms that we've got shown over here that I'm attempting to circle in. Thought I was attempting to circle in purple. Okay, but now it's purple, blue, and black. Okay. We're trying to identify where to place those on our Newman projection. Well, what are they connected to? Okay. Let's take a look at that green bond. Okay. If you're looking at the model, you're looking at the model where that blue atom, or one of the blue atoms, is connected to the front and upwards. Okay, where's that green line? It's down and to the left?
Yeah.
Okay, down and to the left. Well, which of this kind of X in here is down and to the left?
The one on carbon 2. Oh,
Yeah, which would be, because that's carbon 1, that's carbon 2. Is carbon 2 in front or in back?
front.
In front, which means that green line, I need to connect to that front carbon. You laughed kind of in like you're a crazy person.
Oh,
Do you see it?
because you said what
Okay, so you laughed because I was a crazy person. Does that make sense? Does everybody kind of see what's going on with that?
Yep.
If we were to color further out, how about this purple one in our X-Fighter drawing?
It's connected to carbon 3.
Okay, that purple one is up and
To the left.
to the left, isn't it?
Yeah.
That's up and to the left. Is that connected to carbon 2 or carbon 3?
Carbon 3.
Carbon 3. Carbon 3 was the back atom, so I want to make sure that I show that line connected to the back atom. So you'll note that I do not draw anything in that space. Because if I draw anything in that space, I'm now showing the bond connect to the front atom. Okay? So this drawing has 3 dimensions implied within that structure, and we have to be careful with how we look at it. theoretically, you should be able to go through and look at the other side. We've got what I would argue the blue bond and then the red bond. The blue bond will be up and to the right connected to our back carbon. I'm going to erase these 3s and 1s. And then we also have the red bond connected to the front carbon down and to the right. Everybody see it? We could then go through and also make sure that we've got all our labels, our hydrogens on there, specifying those. Kind of, sort of?
So for the Newman projections, there's no need to do the wedges and the dashes because it's already implied.
So in the Newman projection, there's absolutely no need to do wedges and dashes, because if you're looking at this from the end, all the bonds are either coming at you or away from you. None of them are in the plane of the paper. So a solid line is only represented when it's in the plane of your paper. When we're looking at this structure, the paper is running through where my hand is. Okay? There's no bond drawn in that plane. A bond passes through that plane, but none of the atoms are in that plane. Only when we looked at the structure from the side, now the plane of the paper slices through the atoms of carbon atoms, which is why we can show those all connected by solid lines. That was our line angle drawing. Kind of make sense?
Yep.
Okay. So our Newman projection. So cool. We've got that as a Newman projection. We've now drawn one. Right? The carbon 2, carbon 3 bond is what kind of a bond?
Single, sigma.
So single will balk at. You guys already immediately corrected yourself. Fantastic. I would argue that's a sigma bond. And what's special about the sigma bond?
They rotate.
It can rotate. So if you rotate just a little bit, which atom do you want to rotate? Do you want to do the front atom or the back atom? Because we're going to rotate. We don't want to rotate the whole molecule, because then did we rotate the bond? No. So you want to hold in place either the front carbon or the back carbon. I don't care which one. Okay? But for the sake of drawing on the screen and working through all this together, we should agree to something. What do we want to rotate?
Front.
That was the only loud answer. So the front is going to rotate, which means what happens to the back?
It stays still.
Stays the same. Which means as I go through my potential rotations, so we'll erase our starfighter. What am I going to draw for the back? Well, the back is going to be exactly the same. Nothing changes to it. Okay? So I could go through and specify all of that right away. Does that make sense?
Yep.
Right? And now what we're going to do is we're going to take that front atom and we're going to rotate. Because we have gray bonds and one blue bond, it's more clear if we grab just the blue bond, or the blue atom. Which way do you want to rotate? To your left or to your right? I can't believe I'm trying to do this.
Right, to your left.
To my left, thank you. Okay? So we're going to start to rotate. Okay? And where I'm going to stop is right here. Okay? As far as the rotations go, if my math is correct, which it rarely is, we did a 30-degree rotation?
Pretty sure.
Or 60? Okay, it's one of those two. It's either 30 or 60. Whichever one makes you feel better or you think is more correct, focus on that. Okay, so we've done that rotation. Okay, what happens to our front atoms?
They cover the back ones.
They're going to overlap the back ones. Yes, absolutely. Okay, which way do we rotate it?
To the right.
To the right. So if I'm doing this correctly, we would have that be that hydrogen. We good?
Yep.
That was technically a red hydrogen and a green hydrogen. Make sense?
Mm-hmm.
Okay. What we've now done is enough that we could overlay the content from Tuesday. In Tuesday, we said there were two representations we could get for a Newman projection. We could get where all the bonds overlapped, and we called that eclipsed. Or where the bonds all had more space, and we would call it staggered. So we now have kind of two confirmations that we could look at. This is staggered, trust me. And we have, again, eclipsed. Okay? All we're doing is doing a rotation. That's it. So far, so good? Okay. So what we're going to do is continue to rotate. Ideally, I would have shifted everything further over to the left. Actually, I might be able to do that. Are we willing to let me try to shift everything over to the left?
Yeah.
Nope, that didn't do it. Whenever I do it, I always do it by accident. So I don't know how to do it on purpose. Ooh! Are you gonna let me move? Oh! Sorry, I'm pretty excited about that. Oh, you can't see me do it.
I think it's because you had already whited out that side.
Okay, let's try this. Instead of whiting out, let's just erase it. I give up. Okay. So, we've done our rotations, going from kind of our start of our Newman. We rotated to our first rotation, and then what we're going to do is go whoop, whoa. And we're going to go to our second rotation. So what we're going to do is continue that rotating process. Where did we start? Right, we did our rotation to here. Everybody good with that?
Yeah.
Yes, I see your hand. Just let me do my rotation first, then I'll come back to you. Or maybe I need to talk to you first.
I was wondering why they're
Huh?
why are they called B?
Why am I calling it B?
Yeah, because like it's confusing because you're doing H as in hydrogen.
And I'm doing B as in
CH3.
blue.
Oh.
It's not an element.
That's true. But is it the atom on your model?
I guess why would you write it like that?
Color
Are you
coded.
gonna like accept that on a test like blue as the element?
If you were working with a model, yeah. Yeah. Are you working with a model on a test? Probably not. So, to your defense, okay. You're going to make me fix it all. I'll fix it all. Does that feel better? Okay. So we're going to continue to rotate. Remember, we were leaving the back atom alone. So we could draw our back atom, our purple to our hydrogen. We got our blue to our CH3. We got our blue to our hydrogen. Yeah?
Yep.
Okay. What happened with our front atom? Oh, son of a... Oh. Because this was our structure 1, right? Start.
Yep.
Start. Structure 1. Now I want structure 2. Boop. Another 60-degree rotation. Okay. Now what happens when we go through and draw it? Well, again, the back atom does no change. Where does the front B, blue, CH3 end up?
Staggered to the right of the
Staggered to our
bottom
right.
CH3.
So it should be out here, CH3. Right? And note, see the line drawing through to connect to that. Our red hydrogen is now out over here, green hydrogen up. Are we okay with that?
Yep.
Okay, again, I got 2 yeses. We'll work with that. Okay, so cool. We've done our rotation. Are we staggered or are we eclipsed?
Staggered.
We should be staggered. The bonds aren't directly overlapping each other. Cool. So now here's where the butane comes in and messes with things a little bit. Okay? We said there was a difference in energy between staggered and eclipsed, right?
Mm-hmm.
Why? Why was there a difference?
Because the CH3s are farther apart from each other? No?
You're answering the next question.
Oh,
I
sorry.
don't want the next question. Why is staggered different than eclipsed as far as energies?
Bonds rotating.
The bonds are rotated. Why does that matter? Why is this a higher energy state than when it's staggered? What do each of those lines represent?
Hydrogen bonds.
That line does not represent a hydrogen bond. That's in fact a carbon. What does it represent? A bond. What is a bond? Electrons. Do electrons like being near each other? No. So what they will do is they will move away from each other. It's a high energy state to put them in the same space. In our staggered, there is no orientation where the electrons are in the same space. The instant we move into the eclipsed, there's the plane where they overlap that they are in the same space. That's high energy. So when we're talking about staggered versus eclipsed, it's the electron repulsion that's causing the differences in energy. All right? Now we'll bring in the next question that Jen wanted to answer. When we do that one more rotation into structure 2, structure 2 is also staggered, right? None of the bonds are in the same plane. Okay? So it should be staggered. Is it the same energy as our starting structure?
No.
No, why not? Still staggered.
Because
What do you want to try?
Oh, is it down different places? What would the electron?
Take it back to ethane. We're staggered, right?
Yep.
We do a rotation. Oh, they're eclipsed. I continue to do the rotation, and they are
Staggered.
staggered again. Is this staggered different from the first staggered?
No.
No, it's not. They're identical, right? We can't tell a difference. Add our carbon atoms back on. We started staggered, yeah?
Yep.
We did a rotation, it became eclipsed.
Yep.
And then we became staggered again. Is this now a different energy than the first one?
Yes.
Yes. So good. Why?
Because the CH3 bonds are close together.
There it is. And actually, it's not the bonds. We don't care about the bonds.
The electrons.
It's the electrons now on the CH3s are close to each other. And in the previous scenario, those electrons were just close to hydrogens. Well, I can't get away from the hydrogen. That's a default zero state. It's always going to be there. But when I do this rotation now into that staggered, I've brought the CH3s close to each other. Well, why are the CH3s different than hydrogen?
Because there's more electrons.
Carbon is different from hydrogen because carbon has more electrons. It has 6 total electrons versus hydrogen's 1. CH3 not only has the 6 from the carbon, it also has 3 blooming hydrogens on it. And if we had been kind enough as an instructor to add in all of those extra hydrogen bonds, I'm totally going to drop this pen. If we start in our initial staggered state and we spin that, just spin that top one and that bottom one, those hydrogens never see each other, not a big deal. But what happens if we move into the other staggered state? Now when we spin, we could get those hydrogens being really blooming close. Those hydrogens are electrons. They don't want to be close to each other. Because they don't want to be close to each other, that makes this staggered state higher in energy than our starting staggered state. Right? So good job putting in the stupid hydrogens. You win. Kind of makes sense? Right? You may also note that we're now starting to run into a language barrier here. Because we're saying this staggered is different in energy than this staggered. Well, which staggered am I talking about? In both cases, it's just saying this. The only thing that would allow me to differentiate them would be drawing out the structure. Unless maybe I did something else to help me differentiate. Sure. Right idea? We name those different staggered states. Okay? The staggered states are the more relevant ones for what we'll talk about, and we'll hear 2 words that come out to describe them. Staggered anti and staggered gauche, or
I don't know how to
gauche.
say that.
Okay? I think it's more gauche than gauche, and we'll talk an example for it in a second. Okay? Anti, okay? Anti means what?
Against.
What is anti-democrat? Republican. What is anti-positive? Negative. What is anti-top?
Bottom.
Bottom. So what we're talking about with that very first one is we care about those large groups, those CH3 groups. Those CH3 groups, one is top, one is bottom. Those are anti to each other. They're opposite directions. What happens when we move over to the other one? Well, they're not opposite directions anymore, so I can't call them anti. We invent a new term for it. Okay? That new term, Gauche, gauche, however you want to pronounce it, it's pretty sure it's gauche. Has anybody reference anything as gauche? Oh, that's so gauche.
Possibly. I've never used it myself.
Interestingly enough, it showed up in a cult show with, what's her name, the little blonde girl, woman, Kristen Bell, with Hell. Does that ring any bells to anybody?
With who?
She's like trapped in hell.
Oh,
Oh,
The Good Place?
The Good
Good Place,
I haven't
there you
seen
go.
it, though.
The Good Place. She drops a line in there. A student like heard it in that and was like, "Oh, it's in that." And I was like, "Oh, that's interesting." And so I looked it up, and yeah, it is. In any case, okay, what gauche is ultimately referring to is awkward. It's a little bit weird. Okay, the same student provided the perfect analogy for this. Okay, which really maybe only resonates with one person in here, but we'll walk through it anyway. Okay, have you heard of and maybe women have the same culture? I don't know. Okay. When you walk into a men's restroom, there's a bunch of urinals. There's urinal etiquette, if you hadn't heard this.
Oh, yeah.
Okay? When you walk in and there's a bunch of urinals, it doesn't matter. You just pick one and you're fine. The next person that walks in does not pick the one next to you.
The furthest one away.
You would potentially go the furthest one away. It gets more complicated, but we'll just stick with that because it's easy. Okay? You go to the furthest one away. You provide that space. Because if you were in the same space, that's a little bit awkward. That's a little gauche. You've brought the two men peeing next to each other. That's awkward. That's gauche. We don't do that. Okay? And of course, I had to take it to the next level. If we continue to do a rotation, because we're rotating only that front atom, right? So our back atom is going to stay constant all the way through this. What happens here?
They're peeing in the same urinal.
Thank you. See, I'm not entirely crazy for coming up with that suggestion. Okay. Now it's really, really bad. You've got the two, you're sitting there peeing, standing there peeing, and the dude walks in and pees in the same urinal that you're in. That's really awkward.
Should be illegal.
Okay. That is now an eclipsing interaction. Okay. Where they're peeing over your shoulder. That's just not acceptable. Okay? That, just like with our staggered conformations, brings up the same issue that we saw with our eclipsed. What is the eclipsing interaction? In this case, the eclipsing interaction is super high energy because they're right up next to each other. They're on top of each other. These two CH3s are in the exact same space, the things with the most electrons. In our first eclipsing interaction, the CH3 was overlapping a hydrogen in both cases. That's still bad. That's not as bad. Kind of make sense? Mm-hmm. Okay. When we go through and talk about all these different names that we're associating with things, we could go through and also name the different types of eclipsing interactions. Okay. Those just generally aren't as important, and we'll see kind of why in a second, so we don't worry about those. They're eclipsed, varying energies, but they're eclipsed. And then we get staggered where they're anti, complete opposite each other, or we get staggered where they're gauche. Those are our three kind of primary categories. Kind of make sense?
Yeah.
Okay. So we erase all that. Whoop. What do I want to do? I wanted to advance the slide because I believe what we've got is kind of nicely written. Okay. We had our eclipsed. Says eclipsed and our staggered. Those were officially from our ethane. I see you. Give me a sec. Okay, because we don't have our carbons. But if we add in any other atom instead of hydrogen, in this case we're saying X. For the example we walked through in class, what was the X? CH3. Okay, we get two staggered conformations where those staggered conformations are slightly different energies. This first one being where they're right next to each other. That would be gauche. But But I thought gauche was when they were down and to the left, right, off of our previous drawing.
Don't matter.
It doesn't matter where the interaction is happening as long as they're close to each other. That's the important part. Okay, why? There is no up, there is no down, there is no left, there is no right. That's OChem. It's just where you've decided to turn your viewpoint on the molecule. As long as that interaction is there, that's gauche. Anti, they're on opposites. Okay? Gauche will show up pretty much anywhere around in a Newman projection. Anti, almost universally, you'll see on this up-down plane. Why? Humans like seeing the up-down action. Okay, so almost everybody will draw anti where you have your two groups where one's on top and one's on bottom. You very rarely see it discussed off-axis. Can it still exist off-axis? Absolutely. Okay, but our brain doesn't deal well with it, both for the people drawing it and the people interpreting it, and so we tend to not see those ones. Kind of make sense? Okay.
How do you spell gauche?
I'll write it up here next to the thing. I'll write it nicer. So is that clear enough as a G? Okay, just want to check. Because it looks different on my screen. I'm like zoomed in. So we have our gauche, and then we have our anti. Make sense? Okay. So what we're talking about is the different energetics behind this. Some of this actually comes into play when we think about the drawings that we've done. If I asked you to draw butane, 4 carbons, but in a line angle format. Okay? So those 4 carbons, if I asked you to draw that, what would you draw? Ideally, you draw it, but you don't have to. And think about it. What would it look like to you if you were to draw it? Okay? And I would bet that if most of you drew this out, you are not going to draw this. Right? That's 4 carbons. That's butane. That counts. Perfectly valid. Why did you not draw it?
Because I don't like it that way.
Because you're organic chemists and you actually already know a bit of information. You know a bit of information that if I draw it that way and I look at the Newman projection, what does it look like?
Not right.
It looks eclipsed. Okay? The drawing that you picked, where you drew it with that line upwards, is a staggered conformation. Not only is it staggered, it's anti. You're naturally drawing things into the lowest energy state. Most of the time when you draw stuff out, you will draw it in the lowest energy state. We need to be aware what lowest energy state is. That's why we look at Newman projections. Newman projections give us the view to allow us to see those energetics. Our reflex is all ready to draw it nice and pretty in the proper lowest energy state, which I think is fascinating. Why do we just know to do that? That's weird, I think. Kind of, sort of?
Active?
Huh?
Because of active? We're used to drawing it on active like that?
Active is copying us, ultimately.
Oh.
Active did, yeah. Okay? Kind of make sense?
Mm-hmm.
Okay, you think we got it?
Yep.
Yeah? Okay. Because what we'll do is end up making it more challenging, right? Because that's what we always do. Okay? So we'll clear that for a moment. Let's see, how quickly do I make it more challenging? Okay? What we could do is potentially quantify it. This is looking at the exact same system that we just evaluated. Okay? Lots of drawings, but now we're adding a diagram on it. This diagram is saying the rotational angle and then energy for our thing. Okay? So when we go through and look at all of those drawings, does any one of those drawings look, well, let's just see what happens, best to you? Yeah, okay, you're saying yes. Which one looks best to you? Cool. Which one is that? Fair point. Okay. So if we were going to draw this onto our diagram, what are we saying? Okay, well, we're going to draw, matching this straight up above it, just a space to represent this molecule. this rotation. So I'll draw a thing here. We can draw it as a flat line. As we think about chemistry, it's very rarely ever just flat lines. What they are is wells, okay? And rounded wells. Okay? You don't have to stress about that, okay? But that's generally what they are, okay? What happens as no. Right? So now I'm going to ask the question again. Do any of those look best to you? I deleted one, right? Or where? I'm just making sure.
Either the,
Oh, so that's interesting. We already got an either. So now you're saying you're confused. There's two things that are confusing you at least.
the gauche and the gauche, they're just on opposite sides.
Okay? Gauche and the gauche. Okay? Why do those look best to you?
Well, they both have the equal, like, same energy, but it looks neater, and the CH3s aren't as close together as if they were eclipsed, sorry.
There we go. So those are also staggered conformations. Okay? And as staggered conformations, they're lower energy. So we like those. They're nice and staggered. We can see all those pieces nice and pretty. We don't see things overlapping. Are they as low energy as our initial one? No. Okay? So I want to draw those in. Again, there we go. You said either because they're equal. They were the same energy, just on different sides. So we could, again, go through and address this kind of well. Okay? And now's where kind of the fun begins. Okay? If I look at the gauche, okay, the gauche on the left, how do I get that to look like the anti in the middle? What do I have to do?
Gauche on the left?
Yeah, so what am I doing to, whoops, that's an eraser. What do I do to this molecule to make it look like this one?
Rotate the front bond clockwise 120 degrees.
So, wow. Rotate that front carbon atom clockwise 20 degrees. What's going to happen to the energy as I do that rotation? Say that again? Is it going to decrease? Once I've finished the rotation, it should absolutely be lower. But as I'm doing that rotation, is it actually decreasing? No, it's increasing. Because what starts to happen? I have to look like that eclipsed. So as I start this rotation, I'm actually going to go up in energy until eventually what happens?
It bottoms out.
I hit a maximum. It's not going to bottom, it's a maximum. Because then what happens? Now it starts to look like the other one. What happens as I continue to rotate? It's going to go up, again, hitting a maximum, and then it'll bottom back out. Theoretically, it would look prettier than that, but that's close enough. Okay? What happens as I continue to rotate? Well, I'm going to go up in energy again until what?
Tops out.
Till I'm
Yeah.
topped out again. Is that top out again the same energy where I started? Or my other top outs?
Probably.
So now let's take a look at my purples and compare them to this one. Are the purples the same as my green? Not to give away any hints. No, they're different. Why are they different?
Because the green is higher energy.
Green is higher in energy because
Because the pores are.
the methyls are directly overlapping, not methyl versus hydrogen, which means in my energy diagram, what's going to happen is it's going to go up a little bit higher before it tops out. So as we kind of stack this all together, what we're seeing for our eclipsed, I didn't draw that green very well. That's supposed to be the same height. Our eclipsing interactions are peaks, whereas our staggered interactions are valleys. This is important when we think about chemistry because peaks can't exist. Okay? They're a transitional point. In chemistry, everything that exists, as we reference existence, is a valley. So we want to be very careful to label our valleys very well. That's our products, that's our reactants. But how the reaction happens, where the electrons are moving, are now our peaks, okay, kind of above. We'll reference those peaks and we'll predict what they will look like. Ta-da, we're predicting what they would look like. But ultimately, those things don't exist. They can't really exist because you're in a transitional moment. Okay? Those are your transition states, if you will. Kind of, sort of? So we took the same concept that we've already addressed with our pictures, identifying higher and lower energies, and then we just put it into a diagram to represent how those energies are related to each other. We good? Cool. You good? So, ta-da! See, it's prettier. No, it's not prettier. You liked mine better? Thank you. I appreciate that. Okay. You will note in this diagram, okay, they're quantifying a lot of numbers. They quantified a lot of numbers in here. I don't care. Okay, that's not the point. The point is to understand those relative positions, and that's it. That's all you need. Okay. The next part that can happen, we will come back to Newman projections in a second, but what we're looking at is kind of stresses within molecules. With the Newman projections, what we were talking about is this kind of, and I'm always wrong with the term for it, like a torsional strain, because it's the electrons butting up against each other. Okay, in our Newman projection, that causes a rotational stress or a torsional strain in the molecule. Torsional, because what does it want to do? It wants to rotate those groups away from each other. So you'll sometimes hear it called torsional or rotational. It's a strain. That's all I care about. Okay? Make sense? Are there other strains that we can put on a molecule? Yeah. Okay, so what you all could do if you had the model is remove one of those blue atoms. And now what we want to do is see the lower left, it says cyclopropane. To make a cyclopropane, you now need those three atoms to connect. So take one of those bonds and connect it to the blue one. Please do it for me. There you go. You're going to have to remove a bond from the blue one. Or a black one from the blue one.
Okay, there you go.
Right? You should end with something along these lines. Okay? If you're lucky.
You gotta really
Okay.
do it.
And why do I say lucky? You really got to force it in there. Why do you have to force so much? What angle is being generated in a three-membered ring? What's that interior angle? Don't you have to pass geometry?
120?
It's
Wait,
60.
no.
It's 60.
What?
Yeah. Okay, don't worry, I'm not positive on it. I think it's 60, actually, to be honest. Okay, that's 60. Well, why is that a big deal? Well, if we back out of it, oh my God, it's hard to back out of. What is the hybridization of our carbon atom? How many groups of electrons are around that carbon?
SP3. Oh, there's
It's got 4 groups, which makes it
SP3.
sp3 hybridized, which means the bond angle is 109.5. To make the cyclopropane, you have to make that, I want to be 109.5, you have to take 109.5 degree and you have to make it 60. The amount of effort that you're putting in to bend that in is comparable to what's happening on a chemical level. That is extremely stressful for the molecule, and that skyrockets the energy for the molecule. Are you trying to build it? Do you want to build it? You don't have to build it. You've just assembled everything, so I figured I'd try and help.
Yeah, I was trying.
It is very challenging to do. And depending on the model kit that you purchase or decide to use, it's actually impossible. So these ones, number one, I don't care. There you go, make that connection. Yeah, that's
It's hard with
what I do
nails.
kind of good.
I don't want to break it.
Okay. These ones I don't mind on because these ones are so sturdy. Like I said, they'll survive a nuclear blast. That this is not going to be an issue. You can try and force it. And worst case, you break it. Oh well. Not like anybody knows about it.
I was trying to break it,
except
and that's how I
recorded
got
it. But, okay. We've got tons of these pieces. This is the point of trying to do it, and to feel the stress behind trying to make it. And almost always, yes, you'll get it to pop. So like you have to be very careful with how you would go through and do it. As you go through, you could now build butanes, pentanes, hexanes, heptanes. So you're just adding a carbon. Now let's make a new ring. See what happens. See what happens. And what you will find is as you go through and do that, that it gets progressively easier to make that ring. You're building less and less strain in the molecule. That's a new type of strain. That's a strain that I would call angle strain, because you're trying to jam the angle down. Okay? The point here is just to recognize that there's other kinds of things that could factor into the energetics for an individual molecule. That's the big point. Does that kind of make sense?
Yeah.
The next thing that kind of pushes with this, actually, does someone still have the propane, cyclopropane? You got it, Bill. Is not only does our cyclopropane have this angle strain, where we're forcing that bond angle down, but we could also use Newman projections to evaluate this. If you take a look down the carbon-carbon bond, what are all of your bonds doing? They're eclipsing. So not only is there an angle strain on the molecule, I'm trying to crank that angle down, but those electrons are now eclipsing each other, also skyrocketing the energy of the molecule. Right? So what we're trying to do in this process is to just think about the things that could affect the energy of a molecule. Looking at a standard drawing doesn't give you the kind of emphasis of what's happening on how to make it. Oh, I can just draw a triangle. How hard is that? Until you actually try to bend it down, you don't really fully appreciate it. Does that make sense? Okay. As you move through, what you could go through and do for each of these different kinds of rings is look at those Newman projections and try and see what happens to those eclipsing interactions. And what you'll find for a lot of them is that there's a lot of eclipsing interactions. And really there's a big shift away from the eclipsing interactions when we hit the 5 and ultimately really the 6-membered ring. As soon as we hit the 6-membered ring, all of those eclipsing interactions disappear and now everything becomes staggered. So we now lose an angle strain, we lose the eclipsing Newman projection strain, the molecule becomes super stable. You add another carbon, it actually builds more strain. So interestingly, there's a low point in our ring structures. Propane, cyclopropane, high energy. Butane, high energy, but a little bit less high energy, less angle strain. Cyclopentane, we still get some energy issues. Cyclohexane, everything all of a sudden magically balances out and everything works and it's beautiful. You add another carbon and it starts getting messy again. Okay? So that means there's something inherently interesting about cyclohexane. And of course, if there's something inherently interesting about a particular molecule, what do?
Study it.
Now we get to study it. Therefore, you get to learn about what makes it interesting, and that kind of pushes into our next section, if you will. Okay? Okay, everybody hates me with this one. Why are you gonna make my life miserable? I'm not making your life miserable.
Are you talking to yourself or us?
Yes.
What? Both?
All of the above. Okay. Your turn for a little revenge. Can you toss that metal kit at me? Okay. There's only one, so that's good. I was waiting for all of them to come find me, but cool. So what do we have here? Cyclohexane. So in the cyclohexane, if you build it, and I'll pass this one around and I'll try and build some other ones, okay, you'll find that you can actually rotate bonds. With that cyclopropane, could you rotate any of the sigma bonds? No. With the hexane, you can. It does allow for bond rotation. since we get bond rotation, our molecule is now happier because we're allowed to flip things around and kind of flop. That's a good thing. Okay? The more restricted anything is, the less stable it is. Okay? So our hexane will flip and rotate. And what we're talking about, or what we want to consider, is are there energetic things that we need to worry about? Well, as soon as we ask the question, are there energetic things to worry about, what do we need to do? Look at a Newman projection. That's what this is asking us to do. So what we're going to do is take our model, and we need to look down the C1, C2, and simultaneously C5, C4. Okay? I know there's a lot of letters. 1, 2, 3, 4, 5, 6. Yeah? Okay, we want to cite down the C1-2 bond. That was C1, there's C2. You're looking down that bond. Right? That bond has disappeared, right? What does it look like I'm holding on to on that side of the molecule? I know it's a weird question. Work with me. What does it look like I'm holding on to on this side of the molecule?
Butane?
Yes. Give me a little bit more. Because it's connected to a whole bunch of other carbons. Why are you saying it looks like butane?
Because I was just looking at C1 and C2, that was it.
It looks kind of like a Newman projection that we just evaluated. Okay, it's the Newman projection of those things. Okay, why do we need to talk about C5-4? Well, that was 1, 2, 3, 4, 5. What would you see down the 4-5 bond?
The exact same.
You would also see a Newman projection. So when we're talking about the energetics of a chair, we will reference kind of different stabilities of it by evaluating the Newman projections of the chair. Okay? The Newman projection on a cyclohexane is vastly more complicated because I have to draw two Newman projections connected to each other. It's a necessity for that process. I get the Newman projection in my left hand, and I get the Newman projection in my right hand. Can you see? I got 2 yeses from you. Yeah? You're not acknowledging.
It's hard because of your fingers. Yeah, I can see.
Okay. One of the things that's extra challenging with this, and apologies for Nate or anybody rewatching this at home, okay, is that we have to look at the model. And not only do we have to look at the model, do you all see the Newman projections? Right now, you're looking at this, that's what I'm looking for. Do you see the Newman projections? You're like, no, and you're doing this, like where to go? Okay? The Newman projection is a very particular sight line down the molecule. When I was showing it over here, it works because we're now on opposite sides of that line, so you can see it. That's why I had to individually turn to each person so that we can see it. It's very visual and very tactile to the actual model, so it's very challenging to just look at a drawing and be like, oh yeah, that totally makes sense. Okay? Because it won't. Because you're now layering multiple concepts on top of each other. Kind of, sort of?
Yep.
Okay. So, if we were to cite down it, let's see. Oh God, I really did jump to that, didn't I? Okay. Skipped the kind of most important part here. Or not most important part, but a part. Right? So, this is a cyclohexane, right? Cyclohexane. Right? 6-membered ring, you see the hexagon? Everybody got the hexagon?
Yep.
When I turn it like this, do you see the hexagon anymore?
No.
Do you see the Newman projection anymore? No, everything went to hell. Okay? But if you're really lucky, what you should see, a chair. Why you for showing me first? That's where I would put my back. There's where I sit. Yeah. Alright, you guys are already saying yes? Do you see what I'm talking about? There's where I would sit down, or not my sit down, that's my back, lean my back against. So my head would be kind of sitting up here. These 4 atoms are now where I would sit. And I'd have my legs line off there. It's a recliner, like a little recliner chair, a little lawn chair. Are you giving me a hard look? Get a little closer. You got it now? You got it? Okay. The real fun part with this is if we do that, and now say find the chair, you're all just fucking lost. Okay? Because again, it's a very centralized viewpoint, and it takes practice to be able to visualize and see it. So you have to be very, very careful with it. Anybody's video, I don't care how good you think they are, is going to have a hard time explaining it to you because it's model based. Okay? There are conclusions that come out of it. We'll talk about those conclusions in a hot second here. Okay? That you can just kind of memorize. But where those conclusions are coming from is evaluating these different ways to view the molecule. Hint. You got a hint? I know I talked about this.
Does it still have the carbon?
For what's being shown up there, you're right. We don't have the carbons on it. Right? And so we'd be getting something like that where we can see the chair. Well, if we now have a chair, what does that mean you get to do?
Sit down.
It's a fair response. I would argue what you should do would be draw it. Okay? And if you're freaking out about how I got to draw it, you'll see in a second. We'll take a minute to look at it. But before we get there, what I want to do is address this Newman projection. So we're going to turn it so we can see the Newman projection. Right? See if I can actually get the shadow to align. Man, that's really hard. Ooh. Okay, there's a chair. Let's just stick with that. Okay, so we got our chair. If we sat in the chair on the board, where are we facing?
That way.
Yeah, we'd be facing towards what we've labeled as the Newman projection. I just realized I'm really far from the microphone. Okay. So now with our chair, what we're going to do is we're going to sit in our chair. I'll try and use the shadows. I mean, can you see the shadow? Yeah, okay, it was a long shot. Okay. See our chair. Our back is on your left side, right?
Yep.
Which is what it is up here.
Yep.
Everybody okay with that? So we got our chair, and now what we want to do is eyeball down it. Right here. We're going to eyeball down those lines. So now what we're going to do is magically pull it out of the screen. Do you see your Newman projections? Starting to see those? Okay. Those Newman projections are now drawn right here. Okay. You'll note this carbon and this carbon that I didn't show the hydrogens on, I don't care about because they're not in the Newman projection. They're a floater in between. They're the atoms that connects those two Newman projections. Kind of, sort of? Okay. Yes. Yes. I will also have the random parts and pieces up here, and I'll try and assemble as much as I can for that. But yes. So if you have a model kit, bring it, use it so you're used to it. Okay, and then this is the kind of kicker that I really want to end on. So cool, we've got our chair, we're sitting in it. Okay, we're sitting in our chair. I've changed it, right? No longer just a hydrogen, I put a little blue atom on it. Okay? Remember what I said was neat about the six-membered ring? What could it do?
You could shift bonds.
Shift's not the right word.
Rotate.
Rotate. I can rotate bonds. So what I'm going to do is take the back of my chair, my old back. Everybody see I'm grabbing the back up here. This hand, we'll ignore this hand for the moment. We're grabbing the back of the chair, and what I want to do is I want to turn that into feet. So I got a fancy recliner. I can change the direction of where it moves. So I'm going to take that and I'm going to pull that down. As I pull that down, what's going to happen is all of the bonds in the ring are going to rotate. Okay? What am I now holding? Does it look like a comfortable chair?
No.
No, there wasn't comfortable before. There's not a back anymore. Okay? This conformation is what I would argue is the capsized boat. Right? If a boat is just kind of a U shape, it's an upside down U. Trying to get it? Okay, old feet. That's where I put my feet. I want to rotate that up to be my new back. So now when I sit in this chair, which way am I facing?
That way.
I've changed the direction I'm facing. Okay, doesn't matter. Okay, this becomes the hard part and the fun kicker that we can end on. Watch the blue atom. Does it matter?
No.
Where's the blue atom right now? Describe where it is to me.
The outside of the carbon.
outside of the carbon, right? Everybody okay with that? It's outside. Right back over, we'll do the chair. You said no, it didn't matter.
Oh. Never mind.
Where's the blue atom?
Behind the carbon.
Oh, snap, behind the carbon. What does that mean? As we did a sigma bond rotation, we changed the location of the atom. Does that change the energy? Yes. How does it change the energy? How do we know? What do we need to look at to determine energy?
Newman projection.
We would go to the Newman projection, and we would look at all of our fun little interactions within our Newman projection, being, are all of our staggered fun stuff either gauche or anti, and we would say, where do I have the lowest energy conformations shown? Yay! All right, let's end on kind of a good note because Sophia looks like she's dying. Okay? When I have that group floating on kind of the vertical axis of the ring, so if we turn it so you're looking at the ring coming straight in and out of the plane, right? If it's one of those, straight up and down, that's what's known as axial. On the axis, I would argue, of kind of our globe of the hexagon. If we do our ring flip, that's where it's out to the side. Right? That's now on the equator of our globe. That's equatorial. So there's two orientations. There's two substituents possible from our carbon off of a ring. Those two positions are known as equatorial and axial. Okay? Axes are dangerous because they're high energy, right? What is that, Jack Nicholson with his axe and all that fun stuff? Okay? So that's not good. Guess what position's good? Equatorial, because we all want to live on the equator because the weather's nice. Same thing for chemistry. All of our groups will align where they can to the equator of the molecule. So that will be the lowest energy conformation. You can prove that by looking at the Newman projections. But that's the big conclusion that comes out of looking at chairs, is that we get two positions. We label them as axial and equatorial. When you're looking at the overhead view, your axials are either aimed straight at you or directly away. The overhead view, your equatorials technically are opposite the axials, but they appear to be more in the plane of the molecule. Okay? And if we're going to look at a structure, we want to put large groups in the equatorial position. Okay? That's a huge conclusion. We will come back to that on Tuesday. I thought I could conclude that faster than I did.